Today we're going to go through the second midterm from 2017. This will be covering the units on stereochemistry and reactivity of alkyl halides and alcohols. And let's jump right in. First question says, draw examples of each of the following. The first is wanting a tri-substituted alkene. So a tri-substituted alkene is just an alkene where 3 of the 4 possible things that are attached are carbons. So there's an example, 3 carbon groups where the last thing is a hydrogen. A polar aprotic solvent, so a polar aprotic solvent is something like acetone or DMSO or DMF or acetonitrile. All of these are great examples. Pair of enantiomers, these are 2 molecules that are chiral and mirror images of each other. So maybe something like this, PR, and its mirror image. This one's R and this one's S. Pair of diastereomers, these are often cis-trans pairs. So an example could be a trans and a cis alkene. Or instead what you might want to think about is something like this molecule where we have a cis and that which is trans. Meso compound is one with chiral centers and a plane of symmetry. How about something like that, where we have a plane of symmetry here and 2 chiral centers in this molecule? Next question. For the following reaction, select the major product. So in this case, we have a secondary alcohol being treated with sulfuric acid. So sulfuric acid is one that promotes elimination. And because this one is a secondary alcohol and can make a somewhat stable secondary carbocation, and by somewhat stable, I mean more stable than a primary or a methyl, this can go by E1. And E1 will eliminate to give you an alkene, and that means C, D, and E are out of the question between A and B, and this will produce the more stable alkene according to the Zaitsev rule. A is more stable because it's di-substituted, whereas B is mono-substituted. So we will go with A for that first example. Next, we have a secondary alkyl halide reacting with sodium chloride and DMSO. Sodium chloride is a strong nucleophile, and DMSO is a perfect solvent for SN2. So this is going to be a substitution, not an elimination, so A and B are out. E doesn't really make any sense, so we're between C and D, and because this is SN2, SN2 undergoes inversion, so the chloride will be going back if the leaving group bromine is coming in front. So D is going to be the correct answer here. Next one, we have the same secondary alkyl halide, in this case reacting with sodium methoxide, which is a small alkoxide, nice strong base, good for promoting E2 reactions. So this is going to not do substitution with the secondary alkyl halide, it's going to primarily do elimination. So we can get rid of C and D. E is not a possible product in any case. So we have between A and B. Small alkoxides like methoxide will follow the Zaitsev rule as well. So A is going to be our major product here. Next one, we have a secondary alkyl halide, which will react with sulfuric acid to do elimination. Just looking at the product right away, A is definitely wrong because it has a pentavalent carbon. Carbon cannot have 5 bonds. And then we have E, which doesn't make any sense either, which we can eliminate right off the bat. Now what's going to happen with this is it's going to form a carbocation, which looks like this, which is a secondary carbocation, which it can rearrange to make a carbocation which is tertiary, which is more stable, and then this can undergo elimination from this point to give you this alkene as the most stable product, which is C. D and B are possibilities, but they will be minor. The major product for elimination when there's a rearrangement will come from the rearranged carbocation most of the time. In D, we have sodium azide, which is a strong nucleophile reacting with a primary alkyl halide in a polar aprotic solvent. All of these are pointing strongly towards an SN2. So the nucleophile here is N3 minus, and that's going to replace the bromine, which is going to be B. A is not going to be the case. It's not going to go elimination, so C isn't correct. D and E don't make any sense either. So definitely B in this example. For each of the following molecules, indicate which carbon is the chiral center by marking it with an asterisk, and then identify each as R or S. So that's the chiral center here, 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 here. Here, the chiral center will be one where there are 4 different groups attached to a single carbon atom. Now they want us to also identify them as being R or S. So the first one, we can put our hydrogen in back, and ranking priorities, chloride gets 1, the longer alkyl chain gets 2, the methyl gets 3, and the hydrogen 4. You put the low priority group in back, which is already the case. Start from high priority down to low priority, goes around this way. This would be S. Next one, we have a hydrogen here that's in front. And ranking priorities, you're going to have 1 for the oxygen, 2 for the side of the ring that has the double bond, 3 for the side of the ring that does not have the double bond, and 4 for hydrogen. So putting the lower priority group in the back, you can see right now that the way it's drawn has the lowest priority group in the front. So what we can do is just ignore that fact for the moment and go from highest to lowest priority, which is around this way, which is S, and realize that we have it oriented the wrong way. We don't have it oriented with the lowest priority group back. So what we do is just flip the sign of whatever we get, and we have R in this particular example. Next one, we have an amino acid. The top ranked group is going to be the nitrogen. Second ranked group is going to be the carbon with the 3 bonds to oxygen, double bond to the one of them and a single bond to another. 3 for this carbon. And finally, we have 4 for the hydrogen that's in the back. So 1, 2, 3, going around that way is R. And we have the low priority group pointing in the right direction here. In this case, we have a hydrogen coming in front. So again, whatever we get for R or S for this one, we're going to flip because our low priority group is in the front. Top priority is fluorine. Second priority is the side of the ring with the 2 methyls. Third priority is the other side of the ring. 1, 2, 3 goes around that way, and that will be S. However, remember that the hydrogen is in front, so we flip the S to an R. And last, we have this one. This one is actually drawn with the low priority group hydrogen in back, so we don't have to remember to flip anything. In terms of priority, we're comparing a carbon, and a carbon, and so the top rank will be the alkyne group because it has carbon, 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 3 bonds to carbon. Second will be the alkene, it has 2 bonds to carbon, and third rank will be the methyl. So 1, 2, 3 goes around in this direction, clockwise, which means R. If you forget which way around is R or S, just remember, imagine you are turning a steering wheel in that direction. If you turn a steering wheel clockwise, it'll go right. In that case, you'll have R. Next one says, indicate stereochemistry for each alkene by writing E, Z, or neither in the space. So if you look at the alkene and you look at one side versus the other, at the top half of this double bond that we just cut in half, the ranking goes 1 for the fluorine, 2 for the carbon. And on the bottom half, ranking goes 1 for the carbon and 2 for the hydrogen. You can see that the higher rank groups, the fluorine and the carbon, are opposite each other. So this means this one is going to be E. This one, we would attempt to do the same thing, except if we cut this in half, what you'll see is we have same, same. So you can't rank priorities if two of them are the same. If you ever have an alkene where two of the groups on one side are the same, it's not going to be E or Z. It's going to be N. Okay, this one, we have a hydrogen and a hydrogen. Higher priority on the right side will be 1 for the chlorine, 2 for the hydrogen. On the left side, 1 for the carbon, 2 for the hydrogen. Again, the higher priority groups are opposite, so this one is E. Next, we have this compound, and you can see on the bottom side there's a hydrogen not drawn, where we would rank 1 to the carbon, 2 to the hydrogen. On the top half of that double bond, we are comparing a carbon and a carbon, so you'd look to see what's attached to each carbon. That carbon has a double bond to oxygen, which we count as oxygen-oxygen, and then a single bond to oxygen. Whereas the other one over here, we have a carbon bonded to oxygen-oxygen and a carbon. So comparing these two, you compare the first elements, both oxygen, then you go to the second elements, both oxygen, then the third element, and you see oxygen will be carbon, so the higher priority group is the carboxylic acid, lower priority group is the ketone. Higher priority groups are across, so this is E. Last, we have this one, where you can see, if you bisect the double bond, there's a hydrogen here. So the other side will be hydrogen, hydrogen. On the left side, the higher priority group is the carbon, but on the right side, they're both the same. They're both hydrogens, there's no priority. Therefore, this one is going to be N. So this one had no Zs. No big deal. For each of the following sets, indicate the major mechanism. So this first one, A, we have a secondary reacting with phosphoric acid. So phosphoric acid is a strong acid or borderline strong acid which does not have a strong nucleophile with it, so this will promote elimination, and secondary alcohols can make carbocations, so they'll go by E1. B, we have a primary alkyl halide with a really strong nucleophile with a polar aprotic solvent which favors SN2. Everything here is a fantastic setup for SN2. This one is a secondary alkyl halide with a small alkoxide. Small alkoxides prefer to do elimination if they can. If it's a primary alkyl halide, it'll still do SN2, but secondaries will do mainly elimination by E2. D, we have, again, a strong nucleophile in NaSH and a polar aprotic solvent. This is a secondary. These are great conditions for an SN2. Strong nucleophile, negatively charged nucleophile in a polar aprotic solvent. And then the last one, we have a primary alkyl halide with sulfuric acid. Sulfuric acid promotes elimination, but you can't do E1 with a primary alkyl halide because you can't form a primary carbocation. Therefore, this will do E2. Draw complete mechanisms for the following transformations. Show all steps. Include lone pairs, curly arrows, formal charges, etc. So the first thing you need to do here is identify what the mechanism will be. So in this case, we have an iodide being replaced with a cyanide. So this is going to be a substitution because we have a secondary alkyl halide, a strong nucleophile with a polar aprotic solvent. This is going to be an SN2 reaction. You can also tell it's SN2 because you have inverted the stereochemistry where the leaving group was. Okay, so let's draw this out. Let's draw all this stuff, which doesn't have anything to do with the reaction. It says it wants all lone pairs, so let's complete the octet of the iodine. And let's give it some stereochemistry there too. Make a wedged bond. Cyanide is going to be our nucleophile. Remember, if you see NaCN, we need to dissociate it into Na plus and Cn minus. Cn minus has this Lewis structure. It will come and attack the backside of the alpha carbon. The Ci bond breaks, the electrons go onto the iodine, and you make all in one step don't want to do that yet. Cn plus I minus. We would call iodide here the inorganic product, which we don't always draw. Not usually necessary. The next one is H2SO4 with a secondary alkyl halide, and what you can see from the product is there's been a rearrangement. So right away you can tell that this must be a carbocation mechanism, because only in carbocation mechanisms do we have rearrangements. And you can also tell that because it's sulfuric acid and you made an alkene, it's going to be elimination. So you can tell what we want to draw here is an E1. Great. Let's redraw from the beginning. It's not what I wanted. OH, and we'll put our lone pairs in. And sulfuric acid has this Lewis structure. And what we want to do is a proton transfer. Whenever you have a strong acid in one of these organic reactions, usually the strong acid is the first thing to react. So let's get out my red pen, and we're going to draw it like that. This is a proton transfer step. This is now positively charged with 2 hydrogens. We call this an oxonium cation. And we have HSO4 minus, which is the inorganic part that flies away. Now this can then lose a molecule of water now that it's been protonated, because water is a great leaving group. Plus OH to that. This leaves a secondary carbocation. And secondary carbocations are the kind that are prone to rearrangement, because secondary isn't all that stable. If it can rearrange to make a tertiary, that's going to be beneficial for it. And so this will slip over there. And the positive charge will go up where the group came. Realize this is just a single arrow to show this rearrangement. We don't have to have an arrow showing the positive charges moves. We only use these curly arrows to show movement of electrons. This is a good rearrangement because it makes a tertiary carbocation. This is our alpha. We have now 3 betas. And to make the product that we're looking for, the beta hydrogen that we want to remove is going to be over here. We need a base. A decent base to use in this example is water, which we just eliminated in a previous step. So we can do that. Pluck off that beta hydrogen. To make this. This is the major product according to the Zaitsev rule, because it's the most substituted. It's a tetrasubstituted alkene. For the following pairs of molecules, indicate if they're the same enantiomers, diastereomers, or constitutional. First one you can see is a cis dimethyl cyclohexane versus a trans. 1,4-dimethylcyclohexane. Cis-trans isomers are typically diastereomers. This one looks, the second one's flipped around there, but if you rotated it back, it would look like it's rotated back. Basically what we're doing is just curling that one around by 180 degrees, and that would give you this molecule. That fluorine here, this has an R, stereocenter. The molecule on the other side has an S, so if they're an R-S pair, that makes them enantiomers. Same deal over here. We have chiral center right there. You can see that this one, if you looked at priorities, 1, 2, 3, with the hydrogen number 4 in back, is S. And this is the mirror image of that R, so this is also a pair of enantiomers. These ones are Fischer projections. You can see these aren't clear mirror images of each other, so these are not enantiomers. What you see is that the fluorines are together on the same side here, and they're opposite each other on that one. These are a cis-trans pair, which makes them diastereomers. Next, we have 2 alkenes. They're isomers for sure, but the double bond is in different positions. They're not cis-trans pairs, they're not diastereomers or enantiomers. These are constitutional isomers. Convert the following to Fischer projections. So to make a Fischer projection, what you need is to convert the structure into one where everything is eclipsed. So if we leave the left-hand side alone, and we rotate that bond around, we're going to end up with this structure. And if you place your eye up around here and look at the molecule, hydrogen's in back. This is the top of your head, this is your nose, your mouth. What you would see is on the left-hand side of you, you would have the OH groups. Right-hand side, you have the hydrogens. And the top and the bottoms are ethyls, so we need to draw the extra carbon atoms in there. You could flip this around. You could have also drawn it with the OHs on the right. That's basically you just looking at the same molecule from the upside down perspective. Now this one, we also need to draw this one eclipsed. So we're going to flip this one around like so and make the molecule like that. Now this one we're going to be lying down underneath it, looking at it there, so that the vertical groups are the carbons going away from you. Very small forehead here. On your left will be bromine at the top and fluorine on the bottom, and on the right will be the 2 hydrogens. And top and bottom are methyls, so we can leave those as it is. Write the missing reagents. This first one is a dehydration, and for alcohols, dehydration is done with sulfuric acid. Or you could have used instead phosphoric acid. Next one we have elimination. Elimination in this case to form the most substituted product. So this is going to be a Zaitsev. There's lots of ways you can do this, but a small alkoxide would be a great way. Along with the solvent will be the alcohol. So that's all you need to do there. You can't use a bulky alkoxide because bulky alkoxides do Hofmann elimination and give you the less stable product, which is this one. This one's the Hofmann. So to make the less stable one, you would need a bulky base. So something like this, ONA, with the same structured alcohol as her solvent. By the way, for all these elimination ones, heat would be a great thing to add in all examples because heat promotes elimination. Question 9. For bromocyclohexane below, draw both chair conformations and indicate which form is best for an E2 reaction under the conditions given. The conditions are alkoxide, small alkoxide, primary alkoxide. This is E2. So let's get going. We could have the bromine in the up position. Now we want to draw the mirror image. Which would have the bromine still up, but now in an equatorial. This would favor the compound on the right because in terms of stability, the right one is the more stable one. In terms of E2 conditions, for our cyclohexane rings, the leaving group for an E2 has to be in an axial position because that's the only way you can get a beta hydrogen to be anti-coplanar. So alpha, and then this one's a beta, this one's a beta. So if we draw in the axial hydrogens, like so, we'll have some equatorial hydrogens that can't react. You need the bromine to be axial. So this one is good for E2. Of course, it's flipping back and forth when you have this molecule, so both are present. B says draw the E2 reaction mechanism for formation of the major product using the reactive form from part A. Use curly arrows. Great, let's do that. It wants all the lone pairs, so let's put our lone pairs on bromine. Get red lone pairs this time. And we'll get our alkoxide from the first part, which is ethoxide, an ethyl group on there. And there we go. It's going to grab that beta hydrogen or the other beta hydrogen, doesn't matter. It has to be one of the axial ones, has to be anti to the leaving group. That goes there. Electron pairs go there. Didn't give myself a lot of room here, but this will give you double bond here, which is equivalent to something like that. That's it, one step, E2, everything happens all at once. Question 10, for the following multiple choice questions, put the correct letter in the box for each answer. Which of the following solvents is best for SN2? Best for SN2 is polar aprotic, which is A. DMSO is polar aprotic. B and C are protic. E is protic as well, and D is nonpolar. 5, B. Consider the following set of 5 alkene isomers. What's the correct ordering from most stable to least stable? So this is based on degree of substitution. This one is CHEM di. This one is tri. This one is trans di. This one is cis di. And this one is mono. So the least stable is the mono. So we want to pick one that starts with V. So A's out, E's out. The most stable is tri, so we want to have one that ends in 2, which is going to be D. So we go mono, tri is the most stable, and then in between are all the di-substituted ones. Of the di-substituted ones, trans is most stable, and cis and gem are close. So D is our correct answer here. Which of the carbocations will be most stable? So this one is secondary, 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 tertiary, and primary. D is going to be the most stable cation in that example. For the following nucleophilic substitution, which leaving group will give the fastest reaction? So we're looking for one that has the best leaving group, and in this case, D and E are both terrible leaving groups. A, B, and C are all possibilities, but the best leaving group of that trio is going to be iodide, which is A. Which of the following structures is optically inactive? So all of these have chiral centers. So we're looking for one that's meso. So it's not E, it's not D, it's not C. None of those have mirror planes. Between A and B, in order to see if there's a mirror plane, you have to draw it in the eclipsed conformation. So that would look like the methyl down there too. That would flip the OH over. So that does not have a mirror plane. B, however, does have a mirror plane if you rotate it around that bond 180 degrees. So B is optically inactive and it's meso. And we're done.